is going to talk about. Oh, wait, are you recording? Is anyone recording?
Yeah, I saw it's being recorded.
I'm recording.
Oh, okay, you will record it. Oh, okay. I thought I'd record. Okay, sorry. So how is going to talk about generalized symmetry operators from branes. So whatever you want, you can start.
Okay, let me get started. So, hello everyone. I'm Zhang from University of Pennsylvania, and today I'm going to tell you a systematic understanding of constructing generalized symmetry operators from branes. So this will be based on a recent paper I had in collaboration with Jonathan Heckman, Max Whippner, and Ethan Torres. So before starting, let me mention that Ethan and I are both grad students that are in the job application cycle this year for postdocs. So please check us out. Okay. So let me begin by giving an introduction of generalized global symmetries, although I believe many of you are already familiar with this. So the generalization procedure of global symmetry starts by the notion of P-form symmetry, which are symmetry that acts on charged non-topological operators of space-time dimension P. And to be able to account for both continuous and discrete P-form symmetries, the notion of topological symmetry operator is introduced. It is an operator that's supported on a codimension P+1 region in the space-time, which links non-trivially with charged operators. So the term topological means that you can do local deformations on such operator without changing anything. But if you unlink this topological operator with the charged operator, then the charged operator would get a phase. So there are two further generalizations of such notion. The first one is higher group symmetries. It arises when we consider non-trivial mixing between symmetry operators of different forms. And the other direction is non-invertible symmetry, or so-called categorical symmetry. It accounts for the case where a symmetry operator that does not admit an inverse. In other words, if you fuse a symmetry operator with its own complex conjugate, you don't necessarily get identity, but in some cases, you could get a sum of operators. So these are all quite active research directions, especially non-invertible symmetries. So I apologize for not giving a comprehensive list of literature on my slide. But the takeaway we learn from this whole generalization procedure is that the topological symmetry operators are really the modern definition of the generalized global symmetries. Namely, they are the key object that defines such generalized global symmetry. So as people who would like to study quantum field theories from string theory, we would like to see how general can we understand generalized global symmetry via this geometric engineering procedure. So this study has been going on for quite a few years, but it's been taking an indirect approach. Namely, people are able to build this non-topological defect that's charged under such symmetry. So the construction is by taking a brane in the total space-time and wrapping a relative homology cycle in the internal space. So first of all, this QST is engineered by putting string theory on an internal manifold X with asymptotic boundary partial X. And to wrap a brane on this gamma, which is relative homology cycle inside this boundary. And what you get in the non-compact space-time is a non-topological defect, which is infinitely heavy from the QFT perspective. And it carries charge in the so-called defect group or the higher form symmetries. But one complaint one could raise about such way of doing this research is that where can we see the topological symmetry operators built from string theory? And now comes the main point of our work, namely, we can also give brane construction of these topological symmetry operators on the equal footing as those non-topological defect operators. And the main idea is to take the magnetic dual branes and wrap them on boundary homology cycles of the internal geometry. So our new thing is what I draw in red. And this, so the magnetic dual Q brane means that the total dimension of Q is equals to big D minus the dimension of the P brane. So big D minus P minus 2, where P brane is the one we use to build this defect operator. And here, this gamma boundary cycle links non-trivially with this relative cycle gamma tilde, such that the operator M, the symmetry topological operator M we get in the space-time also links non-trivially with this non-topological defect M tilde. So a similar construction has recently arisen in the context of holography or symmetry TFT, and we will make more comments on connections to those constructions towards the end of my talk. Good. So let me give a bit more justification of our proposal. So first of all, I'm starting from a P-brane in the total space-time. We notice that they'll source a dual field strength, which is this FQ plus 2, which is especially captured by this modified Bianchi identity due to the presence of this P-brane world volume. So the idea of from the very first generalized global symmetry operator, generalized global symmetry is that we can get a tentative version of the symmetry operator via integrating flux over the linking cycle ZQ plus 2 in the total space-time. So in our case, it can be written as the submanifold MD of the non-compact space-time times a cone over this boundary cycle gamma, such that it links with the P-brane world volume in the total space-time. So we get a symmetry operator U of ZQ plus 2 written as the integral of Q plus 2 form field strength over this Q plus 2 chain, which by Stokes' theorem can be rewritten as integral of this Q plus 1 form field over this Q plus 1 dimensional boundary of this chain Z, which is now a cycle of MD times gamma. So this is already strong hint by saying that we should consider a magnetic dual brane, a magnetic dual Q brane wrapping on a boundary cycle inside this partial X. I say hint here because you might complain a D-brane world volume action would have more terms, like other than just integral of this single flux. And indeed, I'll come back to this point at later part of my talk. And some other evidences for our proposal includes, first of all, the dimensionality works out correctly. So indeed, if you start from electric and magnetic dual pair of branes in the total space-time, they have total codimension 2, which means that when you wrap them on linking internal cycles, you can indeed get the correct dimensionality such that the symmetry operator M links with the non-topological defect M tilde. And then the fact that the brane is wrapping in the infinity of the internal geometry means that the dynamical or the fluctuating degree of freedoms close to this Q brane will be infinitely far away from this low energy QFT that is supposed to be localized at the tip of this internal geometry. So they all decouple, but only topological flux remains. The third question is, one might wonder if this object is non-BPS as seen from the QFT perspective. Indeed it is, because it is effectively massless from this QFT perspective. But the point is that it takes an infinite amount of time for this object to decay. And even if the decay happens, there will be some topological flux measured by K theory that remains anyway. So these are all evidences that we have to support our construction. And now coming to the algorithmic side, the procedure of finding the symmetry operator in the space-time is to first take the topological action of the brane in the total space-time. So for example, D-brane in string theory or M-brane in M theory. And then we can reduce them on boundary cycles of degree Q plus 1 minus D to get a D-dimensional symmetry operator in the space-time. So the reduction means that we're taking the total Lagrangian density as a cohomology class, and we're doing a Kunath formula reduction of this class into the non-compact space-time piece and the internal geometry piece. And after doing this Coulomb-Fermat reduction, we further integrate the internal geometry piece over the internal cycle that's been wrapped on. And this will give us the general form of this topological operator action. Here I'm being schematic because in principle, we could also get dynamical fields on the symmetry operator, which are supposed to be integrated over. And indeed, such dynamical field will show up in subsequent examples, which I will be working on. And with these actions, we could compute their fusion rules of any pair of them, and therefore determining the general structure of generalized global symmetries. Okay, so before jumping into examples, let me make a brief conceptual remark in relation to no global symmetries in quantum gravity. So recall that in string theory, you can build a quantum gravity by putting it on a compact internal geometry. And here we immediately notice that there are no boundary cycles that we can wrap branes on. And with our understanding, this is consistent with the no global symmetry conjecture, saying that we should not get any type of global symmetry in quantum gravity theories, like no matter invertible or non-invertible. So to look at it closer, we can take a gluing perspective, which is we start by putting string theory on separately on a bunch of non-compact manifolds, which are labeled by xi, each with its own boundaries partial xi. This would give us a collection of quantum field theories, which I could call QFT sub I, each with its own global symmetry. And then we are particularly interested in the case where these xi's can be glued together into a single compact manifold Y with no boundary. In this case, compactifying string theory on Y would give rise to a quantum gravity that is the UV completion of the union of these individual quantum field theories. And in this gluing procedure, the matching conditions of boundary curves and cycles would precisely translate to the physical interpretation that global symmetries of these individual QFTIs are either broken or gauged along this uplifting procedure. This has been showing up in examples in various concrete scenarios, but we sort of give a unified way of seeing this vanishing of global symmetry procedure. Okay. So now let me jump to a very concrete example to illustrate how our procedure actually works. So I'm going to be focusing on a single 61,0 theory, which is this -4 curve non-Higgsable cluster theory. And from non-perturbative type 2b string theory, it's constructed by putting type 2b string on a non-supersymmetric orbifold C2 mod Z4. But then supersymmetry is restored by considering a non-trivial axial dilaton profile, or namely a non-trivial SL2Z bundle over this geometry. So this will mean that along this boundary one cycle, gamma 1 of this length space, there will be non-trivial monodromy acting on B2 and C2. So I further specialize to wrapping D3 brane on such boundary cycle. This will produce for us a 3D topological operator, which corresponds to a two-form symmetry in such 60 superconformal field theory. And later we'll notice that we'll get this two-form symmetry to be non-invertible. Okay, so now the starting point is the world volume action of this D3 brane. So here, these briefs on top of these terms means that we're working in differential cohomology, which is a formalism that combines cohomology with the information of flat differential forms in a concise way. And it allows us to treat cases in which the internal manifold contains torsions. So here, these f of odd degree corresponds to Ramond forms of even degree. And this curly F2 is the difference between the straight F2, which is the world volume Maxwell field strength on the D3 brane, with this B2, which is the NSNS two-form field. And this E term is the Euler density of this S, which will play no role in our analysis. So here, S is really the 3D world volume of the symmetry operator times this gamma 1. And now the Quintet formula decomposition is basically as we stated. And the subtlety is that this world volume Maxwell field strength F2 is dynamical as seen from the perspective of this symmetry operator, whereas other fields will decompose into background fields, which I label in gray. And a technicality is that now that this gamma 1 has non-trivial SL2Z monodromy, it is true that D3 is a singlet under such monodromy. But the subtlety is that, first of all, B2 and C2 field, and then the world volume Maxwell field all transform under doublets of this SL2Z. So we need to do two things. First of all, is we need to add the dual field strength to make our action manifestly SL2Z covariant. And the second thing is that when doing the reduction, we have to use differential cohomology of twisted coefficient to account for this SL2Z action. Like all these might seem a bit complicated, but the take-home point is that we have an algorithmic procedure of doing this reduction and get the symmetry operators, which just take brane wrapping on operator, which just takes as input brane wrapping on boundary cycles and produce the symmetry operator as the output. So let me directly jump to the output, which is the world volume action of this symmetry operator. So it decomposes into this U of M3 turn out to decompose into two parts, where this first part is a simple cyclic group. It is the familiar defect group story in 60 SCFTs that's valued in Z4. So it is an invertible two-form symmetry component. Whereas this U1 is a more interesting component. It is given by this complicated expression, which corresponds to a digraph-Witten theory with gauge group Z2 times Z2. So in particular, these C1 and C1D are dynamical fields that come from the reduction of world volume Maxwell field strength F2 and F2D. So we are path integrating over them. And in particular, this C1 delta C1 terms comes by taking into account the flux non-commutativity of this cycle gamma 1 on which this D3 brane is wrapped on. And more details can be found in these papers of the flux non-commutativity effect. Okay, so the most interesting piece is that the fusion rule of this U1 component with its own complex conjugate is no longer identity, but it is a condensation operator given by all possible insertions of two-form topological operators on this 3D world volume M3. So this would in particular tell us that we have indeed found a non-invertible two-form symmetry in this particular 6D superconformal field theory. Of course, we've just illustrated our procedure in a very simple example. And let me now try to zoom out a little bit. So our claim is that the procedure should apply to all 6D 2,0 and 1,0 SCFTs. And to work out the generalized global symmetry here, we should not only consider wrapping D3 branes, but also possible wrapping patterns of PQ5 branes and PQ strings on the boundary cycles of various degree in all possible ways. And a slight complication would arise for zero-form symmetries, which have to do with wrapped branes so that you produce a codimension 1 symmetry operator in the space-time. And this often have to do with their interplay between the flavor 7 branes that sits in the base of the internal geometry and which further reach the boundary length space of the internal geometry. And there are indeed some technical challenges to treat this strongly coupled PQ objects and get their world volume actions in full detail. But a workaround is to consider the dual M theory picture, where now these PQ label of the strongly coupled objects would translate into wrapping patterns of the same M theory branes on various PQ cycles of this dual torus. So this will be the topic of my next slide. So indeed, another family of example we can consider is 5D SCFTs constructed via M theory. So we're now talking about Calabi-Yau threefolds, non-compact Calabi-Yau threefolds. So I'm schematically illustrating the 5D space-time via 3D boxes. And here, these operators in red, which I label M3, M2, and M0, and M0 illustrate symmetry operators of various degree. And then the M tildes that I label in blue are non-topological defects that's been acted upon by these symmetry operators. So again, according to our general spirit, these symmetry operators are obtained by wrapping M2/M5 branes on various boundary cycles, whereas the non-topological defects would then be constructed by wrapping the magnetic dual M5/M2 branes on various linking relative cycles. So with these, we can similarly do the reduction and compute the world volume action, and then determine their future rules, which we hope to report more progress on in the future. So of course, I specialize to 5D SCFTs because our procedure certainly applies to their higher dimensional analogs like 7D, but in 5D, the structure for generalized global symmetry is richer in a sense that it's known that symmetry of different degree will mix together into higher group. And that's what we will look into in the future. So let me make some brief remark in comparison to the holographic constructions. So basically, in those two nice papers that came up in the August, they consider putting string theory or M theory on a space-time background of ADS D+1 times an internal manifold Z. And their statement is that to build a symmetry operator, they want to wrap branes in topological cycles in Z, but also they have to be placed in a way in this ADS D+1 such that they don't wrap this radial direction, but they are placed transverse to this radial direction. And especially, you need to push them to the boundary of the ADS D+1 to get a symmetry operator. And by noticing that this Z is nothing but the boundary of our internal geometry, we immediately realize that their construction is consistent with ours for overlapping cases, in the sense that their radial direction of ADS D+1 now becomes the radial direction of our internal manifold X. And we briefly comment that from the geometric engineering perspective, our approach is slightly more convenient since it does not require us to explicitly identify the holographic dual theory, nor even show the existence of the holographic dual theory in order to already be able to engineer this generalized global symmetry operator from branes. So as long as we have a geometric engineering construction of the QFT, we would be able to tell you the generalized global symmetries. Of course, this depends on your taste about this comparison. Okay, so a last comment I would like to make is top-down categorical structures that arise from complication of D-branes. So out of active research activity around the 2000, we know that D-brane are a more subtle objects than just having a brane sitting on a particular submanifold of the internal geometry. So they carry their inherent categorical structure, which has to do with tachyon condensations, etc. So in more formal languages, these can be captured by topological string theories. So specifically, the topological A model calls or makes reference to Fukaya category, which basically cares about all possible ways of wrapping branes on Lagrangian cycles of the Calabi-Yau manifold and their possible interactions. Whereas the topological B model talks about derived category of coherent sheaves. So there, the focus is on holomorphic structures. And And the derived category encodes the information of all possible ways to wrap D-branes on holomorphic curves or cycles and their possible interplays. So these top-down structures could very potentially, first of all, unify the fusion rules that we had in previous slide, and then maybe further extend them to enrich the structure. And an intermediate treatment would be K-theory. So first of all, we know that tachyon condensation has a lot to do with K-theory, but then K-theory are also encoded as part of the information of these derived categories. So the reason we say this is because the fusion rule of the symmetry operator is very reminiscent of the tachyon condensation procedure of fusing branes and anti-branes into lower dimensional D-branes. And this procedure is quite well known to be well captured by K-theory. So this is a direction that we hope to also make progress on. Okay, thanks a lot. That's all of my talk, and questions are very welcome.
Thank you, Hao, for your great talk.
Thanks.
Let's thank him with our clap emojis. Is there any question for Hao? We have time for maybe 1 or 2 quick questions.
Eileen.
Yeah, Lynn, you
Hey,
can ask.
Hao.
Hi.
Thanks for the talk. Very good. I had actually 2 questions. So the first one about they're both about the 60 example you gave. So the first one is about this splitting between the invertible and non-invertible part, and I assume somehow the non-invertible part comes from having now the 7 branes present. Is that correct? Because they sort of induce the SL to Z part right before, and then in 2,0 that would not be present. Did I understand it correctly?
Actually, not quite. They basically, so the flux non-commutativity is a crucial factor. So it introduces this C1 delta C1D term. This term has very different behavior from linear terms in dynamical field. So
you mean you say this part is also present in 2,0 theories?
This thing is not present in the 2,0, but I'm saying that this is not very directly relevant to
okay.
This, yeah, it's more of this flux non-commutativity.
Okay, yeah. but okay, then the second part of the question then is, I mean, in what sense does this is a relative theory, right? So in what sense does it make sense to say that a relative theory has a non-invertible two-form symmetry? Or said differently, if I have picked, the polarization, etc., that specifies a flux configuration that is commutative, would this U1 M3 part just become trivial, or will it still remain in an actual absolute version of this 60 theory, non-invertible symmetry? The question makes sense?
Yeah, the question. I don't think so. I think even if you pick a polarization, the non-invertible symmetry should still remain. So
yeah, definitely. The non-invertibleness has to do with the basically fluxes of lower dimensional operators of the theory, and in some sense the standard string defect operators don't see this non-invertibleness at all. They're just seeing a cyclic group acting on them.
Okay,
but there's like, I forget the dimensionality because it's different between the 2,0 and 1,0 cases, but there's like some string like line defects, for example, in the 1,0 that see this non-invertible structure, whether you pick a polarization or not.
Yeah, so basically this non-invertibility comes crucially from the fact of fusing into condensation defect. And this condensation defect, the presence of it is not expected to be affected by picking polarization.
And what are you think get these condensation defects? Is it just the B2 symmetry?
Yeah, it's basically because this symmetry operator not just have a leading term, but also couples to this B2 background field. So
right. So this would be a one form symmetry. So you're condensing one form symmetry on this.
so these B2 background fields are actually sourced by the magnetic dual PQ5 brane. So these two-dimensional topological operators are actually three-form symmetries.
Okay.
So they're codimension 4, and you're inserting codimension 4 things on a codimension 3.
Oh,
and-
okay. Thanks.
Thanks.
Okay. Thank you for your questions. I think it's time we move on to Vincent.
Sure. Thanks a lot.
If there were additional questions or something, we can keep the Zoom meeting open maybe for a few minutes after Vincent's talk, or we can continue the discussion on Slack channel.
Thanks.
So maybe Monkey, you can stop the recording.